Hello everyone, welcome back to Discrete Mathematics and its applications with me Adila Krishnadi. So we continue our discussion on equivalence classes, and now we look at another property of equivalence classes, namely that equivalence classes form the so-called partition, a partition of a set. So what is a partition of a set? A partition of a set S here, so you have a set S, is simply a collection of sets A1 up to A2 and so A1, A2 up and so on, such that each AI is not empty, so these are not empty, and then any two member of this collection, so A1 and A2 or A2 and A10 and so on, if any, the intersection of them would be empty, so they are pairwise disjoint. So any two different member of the partition are disjoint, and then the union of all member of the partition is equal to the set S. Now, of course, from the above definition that every member of a partition is actually a subset of S, right? This is pretty clear from here, right? Now, here is an example or an illustration of partition. So if you have a set S defined and the partition is A1, A2 up to A9, then you could divide here. Yeah, so you see this circle representing S and the partition representing parts of S, and between two different parts you have disjointness. Now let's move to the correspondence between this notion and equivalence classes. So we want to establish this theorem, right? So if you have an equivalence relation R on a set S, then all equivalence classes of R would form a partition of S. That is one direction of the correspondence. And the other direction, if you have a set S and A1, A2 and so on form a partition of S, then there must be an equivalence relation R on S such that each member of the partition is actually an equivalence class with respect to R. So this form the other direction. So essentially the first one would say if you have an equivalence relation, then the equivalence classes would form, the corresponding equivalence classes would form a partition of the domain S. And then if you have a partition of the domain of a set S, you would always be able to find an equivalence relation R on S such that the members of the partition are the R equivalence classes with respect to R. So let's establish this theorem. Let's start with the first one. So suppose you have an equivalence relation R on S, and now we show that all its equivalence classes form a partition of S. That is, we need to show that the equivalence classes of R satisfy the partition. So you need to show that all equivalence classes of R satisfy the definition of partition of S. That is, what are they? 1, all equivalence classes classes of R are not empty. 2, uh, any two different equivalence classes are disjoint, right? And then 3, the union of all equivalence classes of R uh, um, is equal to S. So these are the condition of the partition. So let's show one. So because R is an equivalence relation on a set S, then we could have then it would from it we would obtain equivalence classes, right? So let's say uh, uh, A to be an element of let A be an element of S, uh, and then it must be then this is an equivalence classes, an equivalence class of R, sorry, of A with respect to R. Now, so since R is actually this by definition, uh, set of B such that A comma B is in R, and since R is reflexive, we have that A comma A is in R, so so A is in the class of A, and thus the class of A with respect to R is not empty. Yeah. How about 2? Let A the equivalence class of A and equivalence class of B with respect to R be two different equivalence classes with respect to R. Then by theorem 3, yeah, this theorem, yeah, you know that the fact that A R is different, so from equivalence class of A is different from the equivalence class of B with respect to R, means that A R intersection with the equivalence class of A with respect to R intersected with equivalence class of B with respect to R would be empty. So we have this, right? Disjoint. So these two different equivalence classes will be disjoint. And for the third one, we want to show that the union of all equivalence class with respect to R is actually S. So the we know that this trivially holds, yeah, because well, because this is defined as a set of P from S actually, so set A comma P is in R, and this is obviously a subset of S. Now how about the other way around? So we now show that S is a subset of the union of all equivalence classes. Now this is equivalent to so let X be an element of S. We show that X is an element of equivalence class of A with respect to R or uh, for some A in S. It's not A, it should be S. Now, well, but this is easy, right? Um, because actually, but this is immediate because by definition, yeah, X is an element uh, of itself, of the equivalence class of X with respect to R. Yeah, this is by definition, and the fact that R is reflexive. So that means X is an element of some equivalence class with respect to R. This is for some A in S. So you have that, right? So therefore, all equivalence classes of with respect to R would form a partition of S. Now this establishes the first part of the theorem of theorem 5. Now the second part of theorem 5, we start from partition and we show that there exists an equivalence relation R on S such that each element of each member of the partition is actually an equivalence class with respect to R. So for that, we say let's assume that, so suppose A1, A2, and so on is a partition of S. Now obviously this means that AI is not empty for all I, and then also that AI and AJ are disjoint if I is not the same as J. And of course the third one, the union of all AI is actually S. Now let us define a relation R. R, where R is a set of A comma B from S times S, if and only if, so A comma B is a member of R if and only if both A is in AI and B is in AI for some I greater than or equal to 1. So that is A and B are in the same member of the partition. So now what we need to show is that actually we need to show that R is actually an equivalence relation. Yeah, so it is a relation on S, right? So we just need to show that R is an equivalence relation. So first of all, reflexivity, right? So clearly that, well, A comma A is in R since uh, yeah, so let A is an element of S, then A comma A is in R. Yeah, since of course A is in AI and A is in AI, so it's trivial, right? So then we conclude that R is reflexive. Now, how about symmetry? Uh, let A comma B be a pair such that this pair is in R. Then obviously A is in AI and B is in AI for some I. Thus, by this is the same as saying that B is in AI and A is in AI, right? So it's clearly that B comma A must be in R, right? So um, R is symmetric. Now for the transitivity, let A comma B and B comma C, two pairs that are in R. Then A is in AI, and then also B is in AI, but also by definition C must be in AI for some I. Yeah. Thus of course A comma C must be in R. Right. Thus we conclude that R is transitive. So R is reflexive, symmetric, and transitive. So R is an equivalence relation. Yeah. Um, Now, as a final touch, we want to ensure that because R is an equivalence relation, um, we want to show that we argue that uh, each AI is an equivalence class with respect to R, and this is the same as uh, um, that is AI is some is the same as some equivalence class AR of A with respect to R for some A. um, now by definition of R, we could write so any two element of AI, yeah, are related by R, right? But this means that we could write set AI to be a set of B. Oh, sorry, not this one. Furthermore, AI is not empty by definition of partition, right? So let A be an element of AI. Yeah. So this is for some A element of S. Then AI will be written as the set of of B such that A comma B is in R. Right. So therefore, this is the same as, well, uh, the equivalence class of A with respect to R. So yes, so actually each AI is an equivalence class, an equivalence class with respect to R. So with this, we establish theorem 5, and this allows us to have a correspondence between partition and equivalence class. Now, now let's see how this is applied, right? So let's see an example. The first example, uh, we want to verify that the equivalence classes of this R1 form a partition of the domain natural number. So what are the equivalence classes? What are the equivalence classes of R1? We saw that we have, this consists of this, uh, which is 0, 7, 14, 21, and so on. Which is, well, set of 0 plus 7k, where k is a natural number. Right. Similarly, 1 is a set of 1 plus 7k for some, for k a natural number. 2 would be 2 plus 7k, k is a natural number, and so on up to 6, which is a set of 6 plus 7k. Okay. Now 0, 1 up to 6 are not empty, right? Because at least because obviously 0 is in this equivalence class, 1 is in this equivalence class, and so on. 6 is in the equivalence class of 6. Yeah. And then the intersection of them, take any two, right? Say you could check that, for example, 0 session with 1, yeah, would be empty. Yeah, because there is no way for you to write down, if you have an element of this, an element of the equivalence class of 0, then that element of equivalence class of 0 is divisible by 7, whereas element of equivalence class of 1 is will give a remainder of 1 when you divide it by 7. Yeah, and so on, right? So you check for each pair. For example, 5, 6 is empty, right? All pairs. So all 7 times 6 divided by 2, so 21 pairs of equivalence classes. And finally, the union, right? What is the union of this? In fact, this unions forms, well, a natural number must be in any of these, right? So therefore, this is equal to a natural number. So it is easy to see that the equivalence classes of R1 form a partition of the natural numbers. Now, for the example of the other direction, suppose you have a set S, and the set S is partitioned into 1, 2, 3. So let me just write it down. So 1, 2, 3, 4, 5, and 6. So this is one partition. This is another partition. This is another partition. So you have three partitions. This is A1, A2, and A3. What will be the equivalence relation corresponding to this partition? Well, R, as usual, you define R to be pair of A comma B. This time is from S squared, such that both A is in AI and B is in AI. So they are in the same partition. Yeah, for some I in, yeah, so we have I from 1 to 3, right? So that means we would have, for R, we would have, for example, 1 comma 1, 2 comma 2, 3 comma 3, and then 1 comma 2, 2 comma 1, 1 comma 3, 3 comma 1, and then 2 comma 3, and 3 comma 2, and then you have 4 comma 4, 5 comma 5, and then 4 comma 5, 5 comma 4, and then finally 6 comma 6. It is easy to see. It is easy to verify that R is an equivalence relation. Yeah, so you have this R, right? So these two are examples that show the relationship between partition and equivalence classes. Now we shall end this with two exercises. These two exercises, the first one talks about a set of bit strings with the given relation, and then check if the relation is equivalence, and if so, give the partition of the domain, the set of all possible bit strings due to R. And then here, number 2, you start with a partition, and you verify that these three sets A1, A2, and A3 are partition of Z times Z square. If so, should be partition of Z times Z, not Z times Z square. If so, give the equivalence relation that that yields the partition, right? So we will discuss the answer to this in the next